Alright, so yesterday we looked at the rational theorem, which was just looking at the possible rational roots we could find using the leading coefficient and the tail end coefficient. Today we're going to look at a couple more theorems that have to do with polynomials. The fundamental theorem of algebra and the irrational and imaginary root theorems. These are actually pretty basic, they're not too crazy. Fundamental theorem of algebra, at its simplest form where we're going to be using it, just says that if I look at a polynomial and all of my terms are constant, or my coefficients are all real, then I should have the number of roots I'll find matches the degree of the polynomial. So for this one right here, when it asks state the number of possible roots, ignore complex. We don't use that term. We just look at our degree. It is degree 2. So how many possible roots do I have? I can have two. I'm going to have 2 roots. Okay, so the irrational and imaginary root theorem. This focuses on the imaginary root theorem, but it works for both. And the idea for this is, if you remember in chapter 2, when we dealt with the quadratic formula and we had that plus or minus the square root of b squared minus 4ac, sometimes this would come out nicely. I'm gonna blah blah. This would come out nicely and we would get something like 5 plus 2 and 5 minus 2, and we'd get nice answers like 7 and 3. And that was fine and dandy, and those would be our real roots. But sometimes, or our rational roots. Sometimes we would get gross things. So we would get done and we'd end up with something like 2 plus or minus the square root of 5. I'm just making this up off the top of my head. And what that represented was that we would do 2 plus the root 5 and 2 minus the root 5, but these complex roots, or these, wrong word, irrational roots, came as a partner, a pair. And we call these the conjugate pairs later because it was convenient to have this term for both of these. So what we see is when we have irrational roots, they came in pairs. This also happened when we had imaginary roots. When we did the square root and we ended up like with 2 plus or 6 plus or minus 2i, when we got done square rooting that negative, all that meant is I had 2 roots. I had a root that was 6 plus 2i and 6 minus 2i. I had 2 conjugates here. So what that looks like for what we're saying here is we're going to say if these O's come in pairs, I can never have one imaginary root by itself. If I have this root, I also have this root. They have to come together. So like we did this even with the really simple ones. When I had x squared plus 4 and I solved that, I would get x squared equals negative 4, and I would square root both sides and I'd get plus or minus 2i, but that's 2 roots, 2i and negative 2i. So these O's come in pairs. So the irrational and imaginary root theorem just says that if I have an irrational or an imaginary root, they come in pairs. So for this one right here, what that's going to look like is we're going to look at how many roots could I have. So this one is second degree, so I could have 2 roots. And then we're going to think about what those roots could look like. So for the imaginary roots, I can only have 2 roots, and the roots have to come in pairs. So I could have 0 imaginary roots. That is a possibility. I can't have 1 imaginary root because I have to come in pairs, but I could have 2 roots. So that would be a possibility. So I either have 0 or 2. So, and this being a quadratic, that means it's either crossing twice or it's not crossing twice. There's not a middle ground. Even when we do a multiplicity of 2, if I have the same root show up, we'd still 2 roots. Okay, that means if we look at the real ones, if I look at these possibilities, so for real roots, I could either have, if I have 0 imaginary roots, then I could have 2 real roots. If I have 2 imaginary roots, I could have 0 real roots. So I have to have 2 of each. Okay, looking at another example. Our possible roots here, we just look at our degree here. Our degree is 5. Since this is a 5th degree polynomial, I could have up to 5 roots. Looking at our possible imaginary roots, so for imaginary roots, oops, wrong color. So for our imaginary roots, those O's come in pairs. So I could have 0 roots. I can't have 1 imaginary root. I could have 2 imaginary roots, a plus or minus, or I could have 2 pairs, or 4. So I could have a plus or minus like this and a plus or minus like something else, but they have to come in pairs. So then looking at my real root possibilities, so what's left over, I need 5 roots. If I have 0 imaginary roots, then I need 5 real roots. If I have 2 imaginary roots, that means I have 3 more roots to get my 5. And then if I have 4 imaginary roots, those 2 pairs, then I would have 1 left. So that's what that's going to look like. The purple number can only be even because they come in pairs. The green number is just our degree. And then the red number is just how do we add up to get to that green. So 2 real, no imaginary, no imaginary 2, or no real, 2 imaginary. I could have 5 and 0 to get my 5. I could have 3 and 2 to get my 5, or I could have 1 and 4 to get my 5. Okay, next step, polynomial, getting our possibilities. So this is just applying that rational or imaginary root, or irrational or imaginary root theorem. That just says they have to come in pairs. So we have 1 real and we have 1 imaginary, and this is our problem here. So this one came from square rooting, so then I should have 1 that goes with it. So I have plus 5, or I have plus I, which means I also have a negative I. So I got negative 5 as a root, I is a root, and negative I is a root. Same thing here, we've got 2 roots. We have this imaginary root. It's going to have a partner, a positive I, or just I. We also are going to have another partner, so this one we'll do that in, I don't know, dark blue. This guy also has a conjugate pair. So this came from us square rooting. We did negative 5 plus or minus root 5. So we also have negative 3 plus 5. Oops. Just keep hitting Control Z or Control A. We also have negative 3 minus root 5. So there are our 4 roots. Negative 3 plus or minus root 5, negative I, and then plus or minus root I. So all 4 roots. Now we don't do this with the imaginary root or the normal roots. These ones are okay. So this one's okay. It doesn't have a partner. This one is okay. It doesn't have a partner. And then this one right here is complex or a irrational root. Came from square rooting, and we needed to do the plus or minus. So this one has a partner of negative 2 minus root 5. So this one has 1, 2, 3, 4 roots. Okay, so this is just recognizing that they should always come in pairs if the prerequisites are met. Okay, last but not least, write a polynomial of least degree with an integral coefficient that. Okay, so basically what they're saying is write the simplest version of the polynomial we can make. One thing I do not want you to do is we are going to be doing this in factored form. I'll be able to tell if you do this in photomath, because photomath is going to give you the standard form. I want this in factored form. I know you can multiply these factors out. But we're going to have it, but it's going to look like this. So factored form. So just as a quick refresher from way back when, if I had roots, so like here if I had plus 5, minus 3, and plus 1 as my roots, or as my factors, then my roots would be negative 5, 3, and negative 1. So that's how we're just working this backwards. So we're going to start with negative 5 and say that belonged to x plus 5. If we have 3 as a root, x plus 3, or x minus 3. If we have negative 1 as a root, x plus 1 is a factor that it belongs to. So that's the core of this. So what we're going to look at, and I'm going to, can I bring that down? Okay, so we're going to look for any imaginary or irrational roots. So this one is okay, this one is okay, this one is irrational, so it should be a plus or minus. So we have 1, 2, 3, 4 roots. Now Savis, the book is going to have you multiply them out. Most things are going to have you multiply them out. I don't want you to multiply them out. I don't need you to show me that you have that skill. It's either really simple and you're not showing me anything new, or it's really, really complicated and I really don't need you to be able to do that. So we have 1, 2, 3, 4 roots. Sorry, that's going to bug me. So first one, this one right here, its factor is x. Boop, right there. Okay, x, or for 2, the factor for 2 is going to be x minus 2. That's the factor that belongs to that 0. Now these ones can look kind of scary, but we're going to do the exact same thing. We're going to have 2 factors. We're going to have x plus root 3, but we're also going to have x minus root 3. Now normally, like this is the standard expectation I have for you, is to be able to give me the factored form. If you multiply it out, that would be like a level 5 question where it's a little bit more complicated. This one wouldn't be too bad because this is a monomial, but when you start doing stuff like these ones, it gets a little bit more difficult. All right, so there's our answer. Do the same thing here. I'm not going to do all of these. That one's really similar. Okay, we do the same thing with the 2 i's. So for number 17 here, we have that root. This is an imaginary root. Imaginary roots always come in pairs, so when we square rooted this, we should have gotten plus and minus 2i. Oops, not what I wanted. There we go. So I have 3 roots. There we go. Negative 1, positive 2i, and negative 2i. So let's set her up. So f of x, and then this root gives the factor x plus I. Why are we not? There we go. And then for my 2 imaginary roots, I'll have 2 minus I and 2 plus x plus 2i. Really likes to try and pretty it up. Okay, sorry, I'm not used to this. That's gross. Okay, so there are our 3 factors. X plus 1 has a 0 of negative 1. X plus 2i, it has 2i as a root, or as a, yeah. And then x plus 2i has the negative 2i as a root. Let's look at one more. That one, so this one and this one are going to be similar. Let's just keep with the odds. So for this one right here, we've got no irrational roots. We do have 2 imaginary roots. So we do have 1 imaginary root. it should have come with its partner. Let's see if that works better. We also have this irrational root. This irrational root should have come with its partner 2 plus or minus 2 root 2. So we got 1, 2, 3, 4 roots. This is where trying to multiply it out becomes a nightmare. So let's work our way through these roots. We have the root for 2i would be x minus 2i would be its factor. Negative 2i would belong to x plus 2i as its factor. 2 plus 2i, this is kind of awkward. So the way this works, there's a couple of ways you can write it, but this is always x minus the root, x minus the root. So we're just going to do x minus the root. You can pretty it up if you want to, but that's all I need. This can be, you can distribute that negative if you want. And then last but not least, we have x minus the other root. And these ones are just annoying because the roots are more complex, so it makes them more complicated to write down. Do not multiply these out. This will take you a long time to get through because we have to do 2 binomials multiplied together and 2 trinomials multiplied together. Then we end up with a whole horrible setup. We end up with like a 2-term and a 3-term multiplied together, and it's just kind of gross and it doesn't really accomplish much. So just leave it like that. I'll try and make sure I don't accidentally give you a online assignment that does that. So all right, hopefully that's helpful. Let me know if you have any other questions. I will post this video and this thing up so you can kind of see how it looks, and you can dig through this if you want. Hope you guys are doing okay.